Hi everybody, it's Stephen Moss here, and we're going to do a little bit on the structures so that for the virtualization project, and hopefully all will run well and the technology will be responsive to our needs, and that we will actually get something out of this whole project. So really picking up from the last few lessons in terms of looking at shear force and bending moment, and really to sort of maybe pull into line all of what we've done before. I really want to run through in 3 separate sessions, so you'll actually have 3 videos to watch, and I'm going to split it up into the 3 sections. The first being that we're going to actually calculate the bending moment, the reactions, and then we will go ahead after that and draw the shear force diagram, and finally we will calculate the bending moments and draw the bending moment diagram, and look to see if there are any points of contraflexure on the beam. So we'll kick off and we will start and calculate our reactions. So all along we've been looking at different types of simply supported beams, and here on the screen we can actually see that there's a beam already put on the screen for you, and that's the one that we're going to base all our calculations around today. And as with all along, we're going to go through a series of sort of steps, and I've already given you out a handout in past weeks there, and you should have those steps in your folder, so you will be able to actually follow along with those steps as we proceed. And at any point, if you are stuck, then obviously you can stop the video and put it back to the start again and follow through your notes, etc., and try and gain a better and deeper understanding of what we're talking about if you happen to be stuck at any particular point. So pushing on from there, the first fundamental question that we always ask ourselves, is the beam symmetrically loaded? And obviously we can see straight away from the beam in question is that no, the beam is not symmetrically loaded, and therefore we will not be able to use the sum of the verticals equals 0 to calculate our reactions, and we will actually have to use moments, because obviously there are no horizontal forces on the beam either, and therefore we cannot use the sum of the horizontals equals 0 to calculate those reactions either. So therefore, as I said, we will have to use the sum of the moments equals 0 to calculate our moments. And the first thing that we've got to look at is, are there any UDLs on the beam? If we're going to have to use moments, then if there are UDLs, which you can see here along the beam from A to C, then we will have to convert those UDLs into equivalent point loads. And we do that by taking the load per meter run given here and multiply that by the length of the UDL in question between A and C, and we can see 4 meters plus 2 will actually be 6. So to get the total load here, 12 times the 6 meters will give us 72 kilonewtons, and I'm just going to draw that in here and write up our 72 kilonewtons. Now obviously we need a distance, because anytime we're working with moments it is force times distance, and we need those distances to be given from, I'm just going to pick up here, and I'm going to draw in our distances. There. And there. And obviously we need to write those in. So if it's 6 meters long in total, we know that the equivalent point load for a UDL will sit centrally on the UDL. So it's 6 meters long, so obviously I just need to take that back out, hopefully. Sorry about that. This will be three meters. This will also be 3 meters. So we're now in a position where we can go back and start to actually calculate our reactions. So we're first of all going to take moments about reaction at A. So I'll just put a wee note up about that. We're going to take moments about reaction at A. And we start with clockwise. So spinning around RA, what do we have that's going in a clockwise direction? We've got this converted equivalent point load of 72 kilonewtons by 3 meters. Plus we have this 10 kilonewton times 4 meters away from the pivoting point at RA. Plus we also have this 14 kilonewton point load at the end of the cantilever, and it is 8 meters away. Those are all the clockwise. So we now need to see what we have in an anti-clockwise direction around RA, and what we have is this reaction at C. So we have RC times the distance away from RA, which is 6 meters. We now just have to solve for the reaction at C. So therefore 368 will equal the reaction at C times 6, and the 6 comes across, becomes dividing, so the reaction at C will equal 368 divided by 6, and therefore the reaction at C equals 61.33 kilonewtons. Once we have that completed, we then switch our pivoting point over to the reaction at C, and we take moments about the reaction at C. We do likewise as we did before. We take clockwise first and then equals anti-clockwise. So obviously the first thing we've got to look at is what is going to spin us in a clockwise direction around this point at RC. We've got RA times 6 meters, plus we have the 14 also going in a clockwise direction times 2, and that is all the clockwise we have. So we then look at anti-clockwise, and we can see we've got the 10 kilonewton going anti-clockwise times 2 meters, 10 times 2, plus we also again have this converted equivalent point load, converted UDL, and it's 72 kilonewtons times 3 meters. And again we have to solve for RA. So the reaction at A times 6 plus 28 will equal 236. So the reaction at A times 6 will equal 236 minus 28, because the 8 being positive here comes across and becomes negative. So reaction A times 6 will equal 208 6 comes across, just need to take that out. So that reaction A will equal 208 divided by 6, and reaction A equals 34.67 kilonewtons. Now, we're all aware that when we've calculated both reactions, then we must check those reactions to ensure that we haven't made any errors in our calculations. And this is essential that we do this. So we check reactions using the sum of the verticals equals 0, and we look at the total downward. So we've got 72 plus 10 plus 14 kilonewtons, all acting downward, and that should equal the calculated reactions 34.67 plus the 61.33, and when we total those up, we do get 96 equals 96, and if we take it to our nth degree, giving that this is a plus 96, bring it across, it becomes negative. So 96 minus 96 actually sums up to be 0. So therefore the sum of the verticals do equal 0. So that's our check, and we're now happy with our reactions, and therefore we would be in a position to transfer those calculated reactions onto our diagram. Okay. So let's go back up here, and we're going to put RA in, and it equals 34.67 kilonewtons, and RC we calculated and checked to be 61.33 kilonewtons. And that's us to this point, and so we're going to stop the video for this section. We've calculated our reactions and we have checked them, and we found them to be correct, and therefore we've transferred them now up to our diagram, and the next step will be to draw our shear force diagram and to find the maximum shear force. So that will be on the next video. So once you've watched this and you're competent and confident of what you're doing with it, then you can then move on to viewing the second video. Okay, and we'll speak to you then.